So here is problem 7, also from chapter 15, and it's another half-life problem, really, is what this is. So here we're told that carbon-14 has a half-life of 5,720 years, and it's a first-order reaction. The nuclear decay of an isotope is first-order reaction. It only depends on the concentration of the isotope. If a piece of wood is converted 25% of the carbon-14, then how old is it? So our strategy is going to be here to calculate what the rate constant is for the reaction, given that it has a half-life of 5,720 years, and then just do it for 25%, not 50%. Okay, so I've written this out. So this is first order. And so it's the same thing we just did. Log of A at some time t is equal to minus kT plus the log of the initial concentration. And I've just rearranged that now and put in the half-life. We want to find out how long it takes or what the rate constant is for a given half-life to go to half its initial concentration. So again, those are going to cancel out there. And we just take the log of 0.5, divide it by that half-life, and that gives us a value for K. So let me write that out, and then I'll write out the next step as well. Okay, through the magic of film, so carbon-14, half-life 5720 years. So we went through all that. Let me pull that out of the way. And I've drawn in here. So when I solve this problem, this is what I get. So I put in 0.5. The K for that must be 0.000121 per year. And then it tells us our wood, the carbon-14 in the wood goes to 25% of its initial. So we're actually going to 0.75 or 75% of the initial value. So again, we cancel those, not that bottom one, so we scratch that. And what I want to do is just put that, whoops. I want to just cancel that. And so I take the log of 0.75, now divide it by that rate constant. It tells me what that T is. And my value came out to be 23, I'm writing this with my mouse, so not very good, 78, probably because I didn't carry the right number as it figures through, which is very close to one of the answers. So that's per year, so that's how long it takes to do that, to get to 75%. So that's how essentially carbon dating works as well. So here's problem 8 of the graded homework 2, and you have to read this carefully. So this is a second order decomposition, and it has a rate constant of 2.255. And the question is, how much NO2 decomposes in 4 seconds if the initial concentration is NO2 and it's in 1 liter volume? So we have to do this in molarity, and we're going to figure out what the concentration is after 4 seconds. And then we're going to subtract that concentration after 4 seconds from the initial to find out how much is decomposed. And this is all done at 1 liter volume. So molarity will become the number of moles, which is the answer is. But we have to do this in molarity because that's the way kinetics is. It's in concentration. So let's take a look at if I write out these equations. So second order reaction. This is 1 over A concentration at some time t is equal to the initial, 1 over the initial concentration plus kT. Those values are, that's a 1.33 molar is what that needs to be. And then, so I got to put a molar in there. Let me get that. Molar. I can't yell at you guys if I don't keep my units in there, right? So we do all this 1.33, and then we do this multiplication, and we end up solving then for the 1 over A at that time in molarity. I got that's 0.564 molar. Now that is the concentration of that A. I'm sorry, this is after I've done the inversion. This is the actual A. So you've got to invert what you get for your answer here too. So once I do that, that's my concentration. Now what's left to do is the subtraction. So let me do that for you. So I just went ahead and did that arithmetic, and that's what I get from my A. 1.33 moles minus 0.564 gives me that much mole decomposed.